Going to be looking over the project 9, which is connecting to getting IMU data off our drone over an Arduino sensor, and then going into our Raspberry Pi, and then from there it's piped via Bluetooth to a phone. So let's go forward. So quick overview reminder from last week, we're using our QWINOUT DIY drone. The goal of this week is really just to provide real-time updated IMU data throughout the test flight. Requirements: assemble, demonstrate, pitch, roll, yaw and roll, standard stuff that we've been doing in the past. Capture RPi to be able to display IMU data, to host via Bluetooth, utilize RTOS for the Arduino design, etc. I'm going to quickly buzz through this design and some of the Raspberry Pi attachments. This is just building off of what we've done in the past. So again, here's our drone here. We have our Raspberry Pi attached on the bottom. We're powering it through a mini-PIX power module. Really, this just gives us USB and so forth. Here is our example Arduino code, and really we'll dive deeper into this later on in the next section. But the most important thing is actually how do we configure our Raspberry Pi, and that's really what I want to talk about. So to configure our Raspberry Pi, it's pretty straightforward once you do it once, but that journey to the first time is a little bit tricky. So in general, what I did was I SSH'd into the Raspberry Pi, I ran sudo Bluetooth control, I powered it on, discoverable on, set the default agent, and the commands are right here, set scan on, and then I paired for the MAC address of the device, which for me was my phone, and then I also set the trust for that MAC address. And then I exited, I went to RFCOM, and I released 1 and 0. These are the first two. If you get an error code, that's perfectly fine. That just means they weren't in use to begin with. And then I set RFCOM to watch HCI 0, which is our Bluetooth device. So basically this creates a listening port, and once we actually connect our phone to the Raspberry Pi, it'll immediately recognize, hey, this is supposed to be connected to RFCOM. If you paired your phone, you may have noticed that it connected and then dropped. That's because there was nothing on the Raspberry Pi to actually connect to it. So the phone instructions are pretty simple now that we have our RFCOM watch. Really all we need to do is download the Bluetooth serial terminal app, select the hamburger menu, select devices, and then click on our Raspberry Pi. And then if it doesn't display data, make sure that you have gone in and ran the python main.py file in the IMU reader BLTE code directory. That'll actually basically connect to the RTOS over serial over USB, and then pipe that data into our /dev/rfcom0, and that'll actually make the data display. And this is how that actually looks. So here you can see we have our IMU data. It's comma separated in XYZ format, and it's pretty straightforward from there. So next we'll talk about some of the code. The RTOS code that was used for capturing the IMU data, as well as displaying it on a OLED display. This was done on a seeduino LoRaWAN module Arduino board using a SAMD21 microprocessor. So to kick it off, we include our seed Arduino, our queues, stuff like that, and then our different applications for our different sensors as well. So IMU stuff, and then also our OLED stuff. We then have some constants. We define our SDA and SCL pins. We define our serial stuff. And then we go into our screen info, and then finally we have our global variables. This is what handles our task namings, and then also our queue names for our X, Y, and Z axes. Next we have some RTOS delay functions. I found these all online in the sample code for seeduino's RTOS libraries. So I would recommend taking a look at those. And then finally, our first function is read IMU. It creates a sensor object. It checks that the sensor is actually available, and then while it is available, we actually get the event. We print out that event in a CSV kind of format, and then we send it into a queue. We then yield to our next task, which is going to be this display OLED. This display OLED really creates, similar to the first one, it creates our application or sensor object, make sure it's available, and then we set up our float variables for our X, Y, and Z values. We then say, check that we can actually get those values. If we can't, we pass on them, and then we go ahead and update the display for that. And then once we actually close out, we delete that task thread. And then also, again, we have a task yield here, which basically they just kind of ping pong back and forth between the two tasks. For our setup, we have our serial begins. We check, or we delay for 1 second just to give the USB driver time to come up. And then if you uncomment this, you'll have to wait for a serial connection before it'll actually start up. If you keep it commented, it'll go through. The next thing we do is we set our clock, and then we actually create our queues, and then we print out some helper functions and actually create our taskings. It's important to note that the display OLED is actually the higher task. I found that I got better results with that versus having it as a lower task. And then lastly, our loop is just creating a serial print and prints out if the RTOS isn't running or is in an idle state. This isn't the case for ours because we yield to the next task, and then it actually delays. We're going to see two very short test flights. The first one showing the web server hosting the serial over USB. The second one showing the Bluetooth from the Raspberry Pi to the phone. Two very short flights. Thank you guys for watching.